In this video, I am going to define antiderivatives. So let's consider a function f defined on some interval, I, okay? Now, if we can find a function, let's call it uppercase f, such that when we take the derivative of uppercase f, that means we take f prime, that f prime actually becomes the lowercase f. So we are given a function f that is defined on some interval. If we can find another function which we call uppercase f such that the derivative of the uppercase f is equal to the lowercase f on that interval on I, then the new function that we found, uppercase f, is called antiderivative of f, lowercase f. Antiderivative of lowercase f. Now, this is very simple, okay, not anything complicated. However, this new function that we found not necessarily unique. So if we take the derivative of uppercase f, we get the lowercase f. So uppercase f is an antiderivative of the lowercase f, okay? However, think of this, uppercase f plus some arbitrary constant c. If we take derivative of it, that's going to be f prime plus the derivative of a constant, which is 0. That is f prime. Oh, by the way, according to our assumption, that's also f. So f plus some arbitrary constant is also antiderivative of lowercase f. Now, let me give you some examples. Let's say I have this example. F of x is equal to x. So this is my lowercase f of x. So now we are looking for an uppercase f such that that function, when we take the derivative, will give me the lowercase f. So let's say my uppercase f of x, I define it to be 1/2 x squared. Now let's check it out what happens if I take the derivative of uppercase f, which is going to give me 1/2 times the derivative of x squared, which is 2x. These 2 and 2 is going to cancel. That's going to give me x. So my uppercase f prime of x is x, which, by the way, is nothing but lowercase f of x. So this function, uppercase f of x is equal to 1/2 x squared, is an antiderivative of f of x is equal to x. Technically, we should be adding a constant. Let me give you another example. So let's call it example 1. Let's call it example 2. This time, my f of x is an original function, which is, let's say, sine of x, a trig function. We would like to find another function. When we take the derivative of it, we will get sine of x, which is not very hard to find. My uppercase f of x, if I assume it to be negative cosine of x, as you can see, let's add a constant, plus some constant. So if I take the derivative of it, f prime of x is going to be negative. Derivative of cosine of x is negative sine of x plus the derivative of the constant, which is 0. So that's going to give me f prime of x is equal to sine of x, which, by the way, is equal to lowercase f of x. So this function is antiderivative of this function, sine of x. Yet, let me give another example. Let's call it example 3. Maybe f of x is equal to secant square of x. So now, can we find a function, when I take derivative of it, I'm going to get secant square of x, which is not hard to find. my function is going to be the tangent of x plus some constant. Now, if you take the derivative of f of x, derivative of secant square of x, tangent x is going to be secant square of x. F prime of x is secant square of x, which is just f of x. So this function is the antiderivative of this function, which is secant square of x. Let's get another example. Let's example 4. And this time maybe I will use maybe f of x is equal to 1 over 1 plus x squared. Okay. And let's see, what do I get? My uppercase f of x is going to be tangent inverse of x plus some constant c. As you can see, uppercase f prime of x is going to be the derivative of tangent inverse of x, which is 1 over 1 plus x squared plus the derivative of constant, which is 0. So that is equal to lowercase f of x. So you can see how we can find antiderivatives for our basic trig functions and polynomials and stuff. So let's do an exponential function. Okay. Example 5. F of x is equal to e to the power x. This one is very easy. Why? F of x is equal to e to the power, uppercase f of x is equal to e to the power x plus some constant c, because the derivative of uppercase f of x is going to be just e to the power x, and the derivative of constant is 0, so we don't care about that. That's going to be equal to f of x. So antiderivative of exponential function or e to the power x is the function itself. And I could give you another example involving exponential and logarithm. So let's say my f of x is equal to 1 over x. Then my uppercase f of x is going to be equal to ln of x, or natural log of x, plus c. Now if I take f prime of it, I'm going to get derivative of ln of x is 1 over x plus derivative of constant, which is 0. So that's my f of x. So this ln of x plus c is an antiderivative of 1 over x. Now let's consider another example, general example. So let's say f of x is equal to x to the power n. Okay. In that case, what do? It's easy to find the antiderivative for x to the power n. Why? If you think of this function x to the power n plus 1 over n plus 1, see what happens if you take the derivative of it, plus c, plus constant. If you take the derivative of it, you're going to get 1 over n plus 1 times derivative of x to the power n is n plus 1 times x to the power n plus 1. From that I have to subtract 1. Now this and this is going to cancel out. That's going to give me x to the power n plus 1 minus 1, which is just x to the power n, because this and this cancels, positive 1 and negative 1, which by the way is the function, original function f of x. So this guy is an antiderivative of x to the power n. So antiderivative of x to the power n is x to the power n plus 1 divided by n plus 1 plus some arbitrary constant. So I have defined what antiderivative is. I have given you a bunch of examples of how to find antiderivative of the most basic functions. Now you should be able to find antiderivative. I hope that this discussion was helpful. Thank you very much.